Okay, so here we have the Mr. G worksheet for topic 9.4 resolution. So let's begin at the beginning. And first question says, what is the Rayleigh criterion for diffracted images of two sources to be just resolved? And we can actually see that on the right in the first image A. But basically the Rayleigh criterion, all right, so the sources are just far enough apart, depending on the wavelength, at the central peak of the first source of that single slit diffraction envelope for the first source falls right at the position of the first minimum of the second source single slit diffraction envelope. And of course, this is modulated by that regular old theta is lambda over b, where b is the slit width of each source. But also depends upon the positioning. So actually, the positioning of the sources does not have to do with that equation. I just realized that. So forget I said that. I mean, theta is lambda over b does matter. It still matters. That is what makes the diffraction envelopes. But I'm not sure if that actually applies here for the Rayleigh criterion. There is an equation that does apply, and I think it's a very similar format. Looking for it now. It'll come up later. It's not a big deal right now. But at any rate, let's take a look at picture A. Picture A is what I'm talking about. We can see that the central maximum of the green peak falls right squarely at the first minimum of the red pattern, and the red peak falls just squarely inside the first minimum of the green pattern. This, of course, depends on the wavelength of the light and also the size of the opening for each source. So I just want to make something clear. In my definition for one, it says sources are just far enough apart. When I say just far enough apart, I mean their angular separation as viewed by your eye, say, or is viewed by some kind of camera or whatever. But so that angular separation, we're going to call that theta. They call it theta A. Oh, theta A for theta angular. Really? At least that's what they do in the Sokos book. But whatever. So that theta of angular separation between the sources is the same as the angle of diffraction as caused by the single slit diffraction pattern. And that theta D, that's when we talk about that's which is theta in theta is lambda over b, where lambda is the wavelength and then b is the slit width. And then for a circular aperture, like most cameras, your eye, etc., instead of theta being lambda over b, it's actually theta is 1.22 lambda over b. Now, the 1.22 is not actually explained in the Sokos text. I looked a little bit further into it, and apparently the 1.22 is related to the fact that the intensity is actually described by the Bessel function, and 1.22, or rather it says the first zero of the Bessel function, there's some relation to the 1.22 with the Bessel function and the area pattern. In other words, it's not worth getting into, and we really don't need to go there or even just talk about what a Bessel function is. Just for the level of depth that we require, that we're working at, just know that for circular apertures, theta is 1.22 lambda over b. And you don't even need to memorize that because that's on the data booklet as a formula for you. But that's for a circular aperture. For square apertures, I can't even find anything on that. I'm thinking that the 1.22 is the modulation for the circular aperture, and the square aperture would be simply lambda over b. Because the square aperture is kind of like a slit, right? So then I would just say theta is right, just straight up lambda over b. So yeah, I would not sweat the Bessel function. All right, so let's move on to number 3. And so number 3 says, which image illustrates the Rayleigh criterion, the barely being resolved? We talked about that before. That would be A. And then not resolved means that it's too close. It's closer than what's allowed by the Rayleigh criterion, so that would be C. And then further apart than the Rayleigh criterion would definitely be resolved, and so that would be B. All right, and then we have number 4. And then I think number 4 is kind of obvious. It says 2 ways to increase resolution, decrease the angle of separation of an optical device. Well, I have theta, assuming the optical device has a circular aperture. Most do. I'm going to throw in the 1.22. But we can see that the variables in the expression are wavelength and the aperture width. So if I'm going to increase the resolution, I could change the wavelength, I suppose. Or, of course, so that would, like, by decreasing lambda, I could decrease theta, but I could also increase the aperture size. And this is particularly true of cameras. This is why cameras that have very large openings are able to collect really good detail very quickly, because they can collect more light. But it's not just that they can collect more light, they actually have better resolution. They can see better details that other cameras simply can't. And you'd be like, well then, why don't you just get a bigger camera? Well, that glass costs money, so those cameras are expensive. All right. I will say, before moving on to number 5, this is all the difference when it comes to optical storage for DVDs, which now everything's online. DVDs are becoming antiquated, but the difference between a CD and a DVD, and that the DVD can store movies, and then you have like the Blu-ray DVDs, and basically what they keep on doing with those discs is they use a shorter wavelength. Instead of like a red laser, they use a blue laser, and by using a shorter wavelength, they can get tighter resolution. And tighter resolution means that the tracks can be closer together, the data can be closer together, and they can fit more data on a disc. So they can get better picture, etc., etc. But anyway, so number 5. Okay, so for number 5, we're talking about car headlights, and it says how far can they be away to be just resolved by the human eye. So we're using the Rayleigh criterion of theta is 1.22 lambda over b, where b is the opening size of the aperture. So in this case, it's the diameter of the eye. I'm assuming of the pupil or the iris, or I can never remember, whatever. Looks like the iris, maybe the opening, whatever, of the eye. And also remembering that angle of resolution is also the same as the angular displacement between the two sources. So just to be clear about that, when something's barely resolved, you have the two different sources or slits, whatever you want to call them, but they'll have each one will have its own diffraction envelope caused by a single slit diffraction. And you barely resolve the two different sources when the center of the primary maximum for the second source falls right into the first minimum for the first source. And that diffraction angle, and in that condition, the diffraction angle is 1.22 times the wavelength over b. And so b is actually the size of the opening where the light's coming from. Or I should say where the light is passing through. So yeah, just to be clear, the b in that equation, it's like, so b means like slit width, or the size of the opening that the light is passing through. And so it's kind of like, well, what's b in this case? So b in the case of a person's eye is the size of their eye opening, the size of their pupil. B for a camera would be the size of the aperture, the opening for the camera. So actually, let's kind of go back to the nice little diagram that was provided for us over here. And while I'm thinking of it, I'm using purple and orange here. That's just for illustration purposes. Those are not relating to actual wavelengths. And so there's the center line coming from the iris. And say that's the single slit diffraction envelope from the first source. And then there's a second source out there that passes through the iris. So yeah, kind of redrawing that same situation as before, but now actually using this diagram of the eye. And so the two different sources, they're two different single slit diffraction envelopes are shown at the Rayleigh criterion, where the center of the primary peak, the middle peak, is falling into the first minimum of the first source. And so, but I just want to use this to illustrate point out two things. One is the diffraction angle. So when we're talking about the angle of diffraction, it's this angle to the first minimum. That hasn't changed. So there, that's theta d. But that's the same theta when it's going all the way back to 9.1, where we talk about theta is lambda over b. That is that same theta. So it's really that theta is lambda over b is talking about like the first source, but then for the second source, that maximum, the center of the primary maximum, has to fall right smack in the middle of the center of the first minimum for the first source. So it's kind of like at that angle, it's like if we're talking about this over here, would be like the screen distance, from center line to first minimum. That's the angular displacement there. But the whole deal with the Rayleigh criterion is that the second source's single slit diffraction envelope will fall, the center of that will fall right in the middle of the first minimum from the first source. Now, I wanted to point that out. The other thing I wanted to point out is that when we say B, the size of the pupil right here, that is B. So like that's the size of the aperture for, we call it the aperture, meaning the opening, but that's the size of the aperture for your eye. If it's a camera, it would be the size of the aperture for the camera. Even on your phone, you can take a look at the lenses on your phone, and you can kind of see how large the opening is on your phone. It's not the size of the black circle that covers the entire outside glass. It's the size of the aperture on the inside. It might be a little hard to see. Okay, now that being said, let's see. The other thing I wanted to point out is that this angle, this diffraction angle, is the same as the angular displacement between the two sources that are at a certain distance. So here we're talking about the car headlights, and you have the two different lights, and then there's your eyeball. And so it's kind of like if this is if you're straight on with the first light, and then here's the angular displacement to the second light, there's that theta right there, and that theta between the two different sources is the same as the angle of diffraction. So when those two headlights are just resolved, and so when those two sources are barely resolved, like if you see a car approaching and you just barely see that the headlights split into two, then that angular displacement from one headlight to your eye and the other headlight to your eye, that is going to be the same angle as that diffraction angle actually within your eye as the light passes through your pupil and then on it focusing on your retina. And so here's the setup. You have two different lights, and they're about 3/4 of a meter apart, and we have the wavelength of that light, and it says what's the maximum distance they can be to be just resolved. So where the angular displacement between the two sources is equal to the angle of diffraction for your eye, and we have the size of the eye opening. We have B. It's 1.88 millimeters. So first, let's solve for theta, and then using theta, we can do a little bit of trig and then solve for D. And so we get 3.05555 times 10 to the negative 4 radians. I'm running out of room here. I might want to zoom in a little bit. Then for small angles, tangent of theta is roughly equal to theta. And so that angle that we just found is opposite over adjacent. The opposite is 0.75. We want to figure out what adjacent is. And so we wind up with 2,500 meters away. And that seems kind of reasonable. I mean, you can still see the headlights if they're like, it's 2.5 kilometers away. That's like, a couple miles away, and then just right at that distance, your eye can just barely see, barely split those two headlamps. Okay, let's keep going. Let's take a look at number 6. Number 6 is a different wavelength, a much longer wavelength, and so we have a radio telescope. Okay, so in number 6, we have, so first of all, a radio telescope uses a reflecting dish. It doesn't use, like, its aperture, it's not that light is passing through an aperture like a lens, but for that reflecting dish, that the size of the dish is still the aperture. Like, the size of that dish there represents B. So that's 65 meters is B. And that seems very large, except that the wavelength is also very large. We have a 2 gigahertz frequency, so we can figure out the wavelength from some basic V equals F lambda, where V is the speed of light. So there's our wavelength. It's about 0.15 meters, or 15 centimeters. All right. And then it gives a distance and a separation in light years, and it doesn't even tell you what a light year is. And actually, the conversion from light year to meters is given in the unit conversions in the data booklet. A light year is 9.46 times 10 to the 15 meters. We don't actually need it, because really what we're concerned with is the angle that they subtend. And so, again, very small angle, so tangent of theta is roughly equal to theta, which is opposite over adjacent. So the opposite would be how far apart the two different stars are, and the adjacent side would be how far away they are. So when you do opposite over adjacent, you get a very small angle, 6.74157, etc., times 10 to the negative 4. Now, if we are just barely resolving, then that, and I should have mentioned this was theta A, and so that theta A should be equal to theta D. So let's find out what the angle of diffraction is for this particular wavelength and this aperture of this dish. And I just realized I have to go back and fix number 5, because while I was correct on number 5, I forgot the 1.22 for a round aperture, and this is a round dish, so the angle of diffraction is 1.22 lambda over B. And so when I go for the angle of diffraction, the diffraction limit for this particular radio telescope, I get 0.002, 2.81538 times 10 to the negative 3. Now, the actual angle that the two different stars subtend is less than that. And so since that angle between those two stars is less than the diffraction angle for that telescope is not going to resolve the two stars. It will actually see the two stars as one star. And that's not uncommon for telescopes. I mean, one of the things that when they measure the resolution of a telescope, they talk about binary stars, and it's like, which binary stars can you split into two? And that becomes a resolution issue depending on the diffraction limit of that particular telescope. So, can the telescope resolve the images of the two stars? That's a negative. That would be a no. Now, let's go back to number 5 and fix the numbers. It's going to be close to 2,500 meters, but not exactly. I forgot the 1.22. All right, so this theta A does equal theta D, but that theta D is not lambda over B. We're talking about a round aperture for the eye, so we need 1.22 times lambda over B. So this guy right here, times 1.22 is equal to, so that's fixed. So when I go and solve for my D and my little tiny little thing over here, I gotta fix this guy. I get more like 2011, and if we're only doing two significant figures, because of the 0.75, that is not 2,500 meters, but 2,000 meters or 2 kilometers. Fixed it. My bad. Okay, so here we go with number 7. And looks like another radio telescopes. Another radio telescope. So 7 is an interesting question. It's making reference to something called interferometry, which is using more than one radio telescope to act as like a virtual telescope. But that's when they say, assume the two telescopes together act as a single one with a diameter equal to their separation. That's what they're getting at. And it says, how far apart would they need to be? So basically what they're asking for number 6 is same question, but they're asking what would B be? And what would B be in order for the diffraction angle to be equal to the angle that the two stars subtend? That would be the Rayleigh criterion for barely resolving. As it stands right now, the subtended angle for the two stars is less than the diffraction angle for that telescope. So can we change B? Can we increase B, thereby decreasing the diffraction angle, making it tighter and closer and equal to the Rayleigh criterion angle in number 6? So, okay, so that gives us a B value of 271 meters. So those telescopes would have to be 271 meters apart. And since the original frequency that was given was 2 significant figures, then the wavelength is to 2 significant figures, and so my answer is to 2 significant figures. So I would say 270 meters would be the solution. Next question. Incidentally, that's not just a some kind of fun, theoretical thing that Mr. G came up with. In fact, you can see in the image those multiple telescopes that all seem to be pointing at the same thing. That's exactly what they are doing. They are using long baseline interferometry to act as a larger virtual radio telescope. It's how they took a picture of the black hole in the center of our solar system. Anyway, let's move on to number 8. Okay, so for number 8 is actually topic 12, so we can skip that for now. I'm dealing with de Broglie wavelength, but I can throw together a quick solution just to show, because it's an interesting question. So the work that's being done by the electric field, it becomes the kinetic energy of the electrons, assuming total efficiency. So V is W over Q, so W is V. The work done by the field is voltage times the charge, and that's 1/2 mv squared on the right side, the kinetic energy of the electrons. The reason why I care about this is because I want to get the eventual speed of the electrons, and the reason why I want the speed is because of this thing called the de Broglie wavelength. And then H in that formula is the Planck's constant, which is on the data booklet towards the beginning. I'm actually assuming that, but Planck's constant is a pretty big deal. There it is, 6.63 times 10 to the negative 34 joule seconds. So I need the mass of an electron, I have that, but I need to figure out the speed of these electrons. And so that's going back to over here, where we're going to figure out that speed. And so I multiply both sides by 2, divide both sides by the mass, and square root to get that the speed is radical 2VQ over m. Don't confuse your V's. One's V for speed, the other one's V for voltage, yeah? So then we can throw that into this de Broglie wavelength equation, where lambda is h over mv. H over mv. And so the wavelength is h over mv. If v is radical 2vq over m, then 1 over v is radical m over 2vq. So yeah, de Broglie wavelength is h over mv for the electron. And so we got the speed as radical 2vq, 2 times voltage times charge over mass. And so the wavelength is h over mv. I put in the speed. I put in all the relevant numbers for h and m and v and q. And putting it all together, I get that the wavelength is 2.18 times 10 to the negative 18 meters. And then for number 9, it says compare the electron microscope's resolution with the resolution of a light microscope with observing with a wavelength of 750 nanometers. So resolution depends not just on wavelength, but also on aperture. So I don't really know how that works. I guess we're assuming the same aperture. I don't really even know what an aperture means for an electron microscope. But so assuming the same aperture, I know that the wavelength of light is way bigger, like of 750 nanometers is way larger than 2.18 times 10 to the negative 18 meters. And so that electron microscope is a much higher resolution because its wavelength is much smaller than that of visible light. And I'm looking at 8 and 9, and the 10 to the negative 18, there's something not right about those numbers. That's short, yeah, like the electron wavelength is shorter than visible, but I don't know if it's that short. Still, the electron microscope is a much higher resolution than a visible light microscope, but I think my numbers are not right. I know that the 2.18 might be correct, but the 10 to the negative 18 might not be right. It doesn't matter. We're skipping these two problems. So let's move on to number 10. It's really kind of bugging me on numbers 8 and 9, even though we have to skip them. I know my answer is wrong, and my actual workings are correct. And so I just redid it in the calculator, and I got an answer that makes more sense. So let me just go in there and fix it, otherwise it's going to bug me endlessly. This setup is correct. There's a mistake in here. That's the correct answer. Let me tell you, Miss Coleman told me about the alpha y equals trick in the calculator, and at the time I'm like, yeah, that's cool, I don't really need it. It really helps organize like a lot. It makes like all the difference. And so I knew there was like a math or calculator mistake in there. So 398 10 to the negative 11. The 10 to the negative 18 is short, but it's not, the electron wavelength is not that short. So let's fix that. We'll put in 3. Let me change the color. 3.98 times 10 to the negative 11 meters. And still, visible light is a longer wavelength than that de Broglie wavelength of the electron. So yeah, there you go. 750 times 10 to the negative 9 is much bigger than 3.98 times 10 to the negative 11. So, anyway. Okay, so we're talking about the resolvents of a diffraction grating. And so resolution is not just used for resolving like two different sources, but you can also resolve the different spectral lines that are caused by a diffraction grating. So we know that on a diffraction grating, if you have the pattern that shows up in terms of the maxima that show up on the screen, the positions of those maxima are dependent upon the wavelength of the light that's on it. We know for diffraction gratings that n lambda is equal to d sine theta, and so that wavelength is directly related to, I'm not saying directly proportional, I'm saying is related to the angle, its angular position, where it can be found on the screen. Well, what if you have two different wavelengths? Suppose you're looking at a gas sample, and that gas sample has an emission spectrum, and there are two different wavelengths in that emission spectrum that are very close together. So, like, what happens if the two wavelengths are so close that the maxima that show up on the screen, what if one maximum is within, like, is too close to the other maximum? Like, the two maxima for the two different wavelengths. And so this is kind of the point of resolvence of a diffraction grating. It's like, what if the primary maxima for two different but very close wavelengths are so close to each other that their angular separation is less than the Rayleigh criterion? then they're not going to resolve, right? So they won't individually resolve and they can't be seen. So then what can you do about that? Well, we know that as we increase the number of slits in a diffraction grating, the maxima become more intense and narrower. So by being narrower...
Please click on the shortcut for the morning news.
Click on the shortcut for the morning news. All right, I'll finish my thought after the morning news. So number 10 gets into the equation for what we call resolvence, which is how well a diffraction grating can resolve individual wavelengths, particularly if they're very close together. Like we talk about how sodium has two different lines in it, that we call the twin lines of sodium, and those lines are very close to each other. So the formula is R. R is lambda average over delta lambda. So if I have two different wavelengths that they don't have to be close to each other, but I mean the whole point of resolvence is that you're trying to resolve two very close wavelengths. So if they're not close to each other, then you don't need a high quality diffraction grating. But at any rate, it's and it's also dependent upon like what kind of wavelength we're talking about here. Are we talking about a long wavelength like red light, or are we talking about a short wavelength like violet light? So if I have two different wavelengths that I'm trying to resolve, say like lambda 1 and lambda 2, then the resolvence of a diffraction grating is the average of those two, and the formula on the data booklet just says lambda. It's the average of the, like when we say like lambda over delta lambda. Well, what's delta lambda? Delta lambda is the difference between these two wavelengths, right? And then the lambda at the top of the expression, where it says R equals lambda over delta lambda, that's actually an average. I don't know why it doesn't say average. It should, but it's an average of those two wavelengths that you're trying to resolve. And you can see that R and delta lambda are inversely proportional, meaning that the better the resolvence of the diffraction grating, the tighter the delta lambda that you can resolve. So the closer together the lines are, that you can actually see that they have two different lines. Now, this is dependent on, it's like, okay, that's fine, that's what resolvence is, but what does that have to do with the diffraction grating? And actually, as you increase the number of lines for a diffraction grating, you can actually increase the resolvence. And the reason why that's true is because... So remember from our talk about diffraction grating that if you increase the number of slits in the diffraction grating, the maxima become more intense and become tighter, like more narrow. It's like, well, if they're more narrow, then there's less of a chance that the maxima of one wavelength is going to fall within the first minimum of the other wavelength. And so then you'll be able to resolve the two wavelengths that are closer to each other. And that right there is the answer to number 11. So yeah, like I said, increasing the slit count makes the maxima tighter. It really decreases the diffraction angle. So that means that fringes can be closer together and still resolve. Now, the resolvance is also proportional to the order of the maxima. So number 12 says, explain why resolvance is proportional to the order. So basically, as you move away from the center line, not only are the fringes are going to be separated based on wavelength, but as you move away from the center line, that separation between the fringes by wavelength is going to get larger. So yeah, the fringe separation increases, but that's on a flat screen. Let me see if I can draw that to illustrate why that's true. And the nice thing about explaining everything is I can just take a little spot and just make it bigger for my drawing space. Okay, I pulled out the straight edge and the whole 9 yards for this guy, but I showed a, based on wavelength, that red is going to have a broader pattern and blue is going to have a tighter pattern, but the angles are the same. So the angles between the, say, like red and maybe orange or yellow for the first order will be the same as the angle for the second order. So if this was shown upon a semicircular screen, then there would be no difference in the fringes. But if you have a flat screen, which is how it's usually projected, you are kind of slicing that radial pattern with a line. And so what happens is that as the orders increase, if I kind of like the first set of line was first order and the second set of lines was second order, all of the angles are the same, but as you slice that radial pattern with a straight line, then the spacing between the fringes increases. I can tell you that just based on this diagram that I just drew, I'm measuring with my ruler here, and for the first order, I'm just right here on my iPad screen. I can see that the colored lines are about 5 millimeters apart. Like for instance, 5 millimeters between the red and orange lines for the first order. But then if I put down a ruler between the red and the orange lines for the second order, that's about like 8 millimeters. And so basically, as I increase the orders, they're going to spread out even more. So like I wrote for this answer, as you move away from center, from the 0th order, the fringe separation will increase. But if the fringe separation is increasing, those fringes might, the separation might increase to the point where two fringes that were not resolvable because they were too close together on a lower order set. So yeah, so fringes too close to be resolved in a lower order may be resolvable in a higher order because in the higher orders, the fringes spread out more. So there you go. All right, so 13, what's the resolvence of this diffraction grating? We have the two different wavelengths, and they say that they are visible. And so the resolvence is the average of the two wavelengths over the difference between the wavelengths. Now, I did not convert back from nanometers to meters because resolvence is actually unitless. If it's wavelength over wavelength, it's meters over meters, and so the units kind of cancel out. So we're going to have nanometers over nanometers, and so the units cancel out. There's really no point of converting back to meters. And so we get a resolvence of 459. And suppose when you subtract the two different wavelengths, you technically only get one significant figure in the denominator, so maybe that answer should really be more like 500, but I hate working with numbers with one significant figure. So I'm going to hand wave the significant figures and say 459. There's the bell, and so number 14 will have to wait. So number 14, the minimum number of lines under the beam to resolve the order 2 spectrum. So we already have the resolvence from number 13, that's 459. And so we're going to say resolvence is NM, where M, the order, is 2, and we're going to solve for N. So then 14 says minimum number of lines under the beam to resolve the second order spectrum, and you're going to need 230 lines under the beam in order to resolve the second order spectrum. Assuming that we're having, for number 15, I'm assuming that it's going to be the same number of lines under the beam, and using that, they're like, well, okay, but will the first order spectrum be resolved? So I'm trying to figure out number 15. It's kind of a weird question because number 14 says, what's the minimum number of lines that you would need to just barely resolve the second order spectrum? But as we increase the orders of spectra, then those fringes spread out. So then if it's 230 lines to just barely resolve the second order, then no, the first order is not going to resolve because you just barely resolved the second order. I mean, I can also show that with the equation. So yeah, in 15, I'm not really sure what they're getting at, but my logic is that no, the first order spectrum will not be resolved because R equals Mn, and we just found that the number of lines is 230, assuming it's the same number of lines under the beam for the first order and for the second order. I didn't change the diffraction gradient, I didn't change the beam. So if that's the case, if m equals 1, then r is 230, which is less than the 459 that you would need to just barely resolve the delta lambda between these two wavelengths in number 13. So I think that I don't really understand what he's getting at in number 15, because if 14 is giving an n value, a number of line value, for just barely resolving the second order, then no, the first order won't resolve. The third order will, and the fourth will. But if second order is just barely resolving, then any orders beneath second will not resolve. Maybe that is the point of 15. Whatever. 16. Lines per millimeter. So this is where the beam width comes in. And so if we have 230 lines being illuminated by a beam of 0.45 millimeters, and so 16 says minimum number of lines per millimeter. Well, the beam is 0.45 millimeters wide, illuminating 230 lines for the second order. And so 230 over 0.45 is 511 lines per millimeter. I guess if they wanted the first order to also be resolved, then it wouldn't be 230 lines. It would be 459 lines. And so that's 459 over 0.4500. And that would be 1020 if you want to resolve order 1. So there you go. All right. Let's see, we have 17 and 18. Are these the last questions? They are the last questions. So we have a spectroscope. So let's take a look at our spectroscope. Okay, 17 and 18. 17 says, what's the smallest difference in wavelength, the smallest delta wavelength that can be resolved in the fourth order for this spectroscope? They give us the size of the grating, they give us the number of lines per millimeter, and they give us the average wavelength coming in to the spectroscope. Well, we have our formula is going to be lambda average, like R equals, which I don't need the R right now. Let me write like the whole thing, hold on. So the resolvance is lambda average over delta lambda, which is equal to the order that we're looking at times the number of the lines. And we don't have the number of the lines. We have the line density. We have like 725 lines per millimeter, but we also have the size of the grating. So using the size of the grating and the lines per millimeter, we can figure out how many lines are being illuminated, assuming that the entire grating is being illuminated by the light. So let's see. I'm going to kind of do it off to the side over here. The grating size is 2.35 centimeters, and then there's 725 lines per millimeter. And so let me do a little zoomy zoom to give myself enough room to figure this out. So 17,037.5 lines. I'm going to round that to the nearest line. And I mean, as it is 725 lines per millimeter, I should probably just round it to 3 significant figures, but I'll round at the end. But there's no such thing as like half a line, so at least I'll round it to the nearest whole number. All right, let's take a look here. We're looking for the delta lambda. So delta lambda is lambda average over mn. And so we have the average wavelength, we have the order, and now we also have the n. And I am not going to convert back the wavelength from nanometers to meters because my answer is a delta lambda, which will also be in nanometers. So I'll just leave it in nanometers and we'll go from there. And so I get a final answer of 0.00697 nanometers. So like, let's see, that would be 6,000ths of a nanometer. That seems very tight. Let me take another look at my numbers. Yeah, the numbers check out. I guess that's just a really good spectroscope then. But anyway, even if my math is wrong, that's how you approach the problem. And then resolvance of the grating, I mean, I pretty much did all that work already. I know, let's see, well, actually, it doesn't matter what order Since now that I know what delta lambda is, why don't I just do lambda average over delta lambda? We get about 68,000 for the resolvents, and to three significant figures, we'll say 68,100. And that's the last question.